One of Go's many strengths is its ease of cross-compilation. You can cross-compile Go programs as single binaries, targeting several OS and CPU architectures, all from the same codebase. No additional runtime required. Hi, I'm Justin Walker. I'm a software engineer at Walmart Global Tech, and I'm here today to talk to you about that last option. So during the course of this talk, I'm going to give you a short introduction to the Syscall and Unsafe packages, particularly the Unsafe pointer type. I'm going to teach you how to load the Windows API functions and then call those APIs, which will involve mapping C types to and from Go types. It will also involve memory management, both memory managed by Go and also unmanaged memory that comes from C. And throughout the course of this talk, I'll be providing practical examples that demonstrate these concepts. But before we begin, let's travel back in time a little bit. Now, for those of you who do get the reference, I'm very sorry. I did not license Paul Engelman's Push It to the Limit for this talk, but just use your imagination. So in 2016, much of the infrastructure that I worked on was on the Microsoft Windows platform. We were running .NET microservices, and we had an in-house job scheduler and deployment system that used pre-allocated clusters of VMs allocated to each team. Like many companies, we wanted to move to a job scheduler to reduce the cost of our infrastructure by abandoning the single tenancy model. We also felt that moving to a well-supported open source solution would increase the maintainability of our system overall. There were so many job scheduler options to choose from at the time, but only if you were on Linux. We found that HashiCorp Nomad worked for us since we could run raw executables natively. And this was great, but moving to a multi-tenant platform meant that the noisy neighbor problem would become more prescient. So we wanted a way to isolate our services from one another. However, unlike Linux, the container story on Windows was not really that great. At the time, they were only in preview. The .NET images were especially large, on the orders of gigabytes. They also had an interesting portability quirk, where depending on the system that you built the image on, would limit the system on which you could run that image. So they were inexorably tied to the platform on which they were built, which was not really an issue on Linux. So for these reasons, we decided early on that we did not want to rely on the Windows containers to run our applications. But we still wanted some way to isolate our microservices from one another so they wouldn't monopolize the VMs on which they ran. I found that the containers were actually using a pre-existing concept called a job object. That gave us the ability to constrain the amount of resources that were given to a single Windows executable, thereby allowing us to safely schedule these processes together, knowing that they could not use more memory or CPU than we configured for them. Now, this was great. However, those APIs were just out of reach. Neither the Syscall package nor the golang.org access Windows library implemented the functions that we needed to call these APIs. So we had to dig in and find out how to do this ourselves. Now, this talk summarizes the techniques I learned from the standard library and other libraries that were working with the Windows API at the time. And I hope that by presenting this to you, you don't have to go down that path and discover these things yourself, and that you can use the lessons we learned to call those Windows APIs. So our first introduction is to the Syscall package, and you're probably already familiar with this. It's your gateway to the OS. It provides some OS primitives to talk to the OS kernel directly through Syscalls. But unlike Linux, Windows doesn't really have a Syscall concept. All right, well, that's not entirely true. It does, but Windows Syscalls are undocumented. Instead, you must use the Win32 libraries that come with Windows to access these things on your behalf. Now, those DLLs may in turn interact with other DLLs and system services, but they will eventually access the kernel and get you the result you need. The point is you can't go to the kernel directly. So because of this, Windows Go libraries actually use the Syscall library to load those DLLs and call those functions, much like you could with CGO. But you don't have to use a C compiler and linker to do it. Now, a little bit of warning on using the Syscall package. You should always guard your use with a build tag. This is another Go proverb. So if you're building for Windows, you want to do a build tag to limit the build on only the Windows OS. And also, you could use the file name to do the same thing. Moving on to the unsafe package. With the unsafe package, there are no guarantees. And this is because unsafe contains operations that sidestep around the type safety of Go programs. It does this by allowing you to manipulate pointers directly using the unsafe pointer type. The unsafe pointer type allows you to convert between a regular Go pointer to unsafe pointer and back, maybe even to a different pointer. The unsafe pointer also allows you to convert to a uint pointer, which is just a number, and then from a uint pointer back to an unsafe pointer. So using the unsafe pointer allows Go programmers to perform things like pointer arithmetic and converting from a pointer of one type to a pointer of another type. At the boundary of C and Go, we'll be using these unsafe operations quite a bit. So here's an example of something you can do with the unsafe pointer type. You can convert between two pointers of different underlying types. For example, we have a type T1 and a type T2. They actually allocate the same amount of memory. T1 allocates 4 bytes of memory using a single struct field A. T2 allocates 4 bytes of memory, just like T1, except it divvies this up between two subfields A and B, each allocating 2 bytes. So the size of T1 and T2 are the same, and this allows us to convert from a pointer of T1 to a pointer of T2 safely using the unsafe pointer conversion. So we get a pointer to T1 using ampersand, convert the resulting pointer to unsafe pointer, and then use the cast to type pointer T2, and finally we can actually dereference that type to get a value of type T2. So this is how you could convert between T1 and T2, kind of like C does a reinterpret cast. We're reinterpreting what underlying type that pointer points to. Another thing you could do is pointer arithmetic. So in this example, we have a 3-byte array of data. We set up a pointer to the first element of that data. And this is much like how C arrays are defined. It's just a pointer to the first element. So we can use pointer arithmetic to advance where our pointer is pointing to get to the last element. This is done by converting the pointer to our first element into an unsafe pointer, then to a uint pointer to make it into a number. We can then add 2 bytes and then use our conversion from uint pointer to unsafe pointer to convert it back to a pointer to a byte. And now we can have a pointer to the last element of array. And if we dereference that value, we get the last value of that array, which is 3. But since Go is a garbage collected language, there are no guarantees that Go pointers you deal with won't change their physical location in memory. But Syscalls, they still need to access the physical address from memory. So conversion of a Go pointer to an address requires special care. The Go compiler will help you with this, but only if you follow a strict set of guidelines when converting Go pointers to uint pointers. Now, this is covered pretty exhaustively in the unsafe package itself, but if I were to boil this down to a couple of rules, it's really to never store the result of an unsafe pointer to uint pointer conversion in a variable before using it. Also, just don't point to memory outside of allocation boundaries. So here's an example of doing those things that I mentioned were bad. We have our same data array of 3-byte elements. Instead of converting to P1 directly, we are instead going to convert to a uint pointer and then store that into a variable. Now that variable is just a number. And so by the time we get to P1, that number may no longer be referencing memory anymore, allocated memory that data was at. It may have been moved. So when we convert that back to a pointer to a byte, we may be pointing to unallocated memory. Now, GoVet will usually catch a problem of this nature. The other type I mentioned is allocating past boundaries. Now, this is trivial here. We just add more than one element than we have in our data array, and we're trivially beyond the boundaries of our underlying allocated type. But You could also consider this as casting a pointer to a value that has a larger underlying memory model, in which case you're still accessing memory beyond the boundaries of the underlying allocated memory. And in my testing, I don't think GoVet caught this. So next, we'll move on to how do you load the API functions that you're going to be calling. So the first step in doing this is finding out if you need to do it at all. Many of the Windows API calls are implemented in the golang.org/xsyswindows library. Though the stated goal of the library isn't really to cover exhaustively every possible Windows API, I mean, that API service is really, really large. It's been around for a long time. But if you find the API calls you need in this library, it should be your first option. Don't do all this work I'm outlining unless you really need to. All right, so you've looked at the xsys package. It doesn't have the API call you want. So now what? Well, you have to construct the call yourself, using the Syscall and the Unsafe packages to interface between the Go types and the C types. The DLL and type signatures of all functions can be found in the programming reference for the Win32 API at docs.microsoft.com. And this will likely be your only way of figuring out which API calls are available, unless you have access to the Windows source code or a friend in Redmond, but I don't think much of you have that. So us layman's will be going to docs.microsoft.com. So as an example, let's see what the type signature is for CreateJobObject. And whoa, we actually have two different signatures. We have a CreateJobObject A and CreateJobObject W. What gives? Well, in the Windows API, these functions accept strings. And strings in the Windows API, by and large, come in two flavors. They come in the ANSI C variety, which are just 8-bit characters with a null terminating byte. This is just for like passing ASCII characters. However, if you want to support Unicode, there is a variant that's usually suffixed with W. These are for wide characters. Now, unlike Go, UTF or Unicode is actually implemented underlying with UTF-16. So you're not passing UTF-8 characters into your functions. You actually have to do some conversion to UTF-16 first. And we'll come back to how you do this in a bit. But first, we need to know, how do we load these functions? So the Syscall package actually has a couple of functions you can use to load DLLs. It has a new DLL function and a lazy new DLL function. Now, the lazy variant only actually loads the DLL when it's used for the first time, basically when you call the procedure from a DLL that's loaded this way. And this, if you use the lazy variant, this can probably help with startup times. If you don't actually access the Windows APIs up front and you want to defer loading them until you absolutely need them. But the Syscall package is actually subject to preloading attacks. Basically, what these are if the DLLs that you're loading have the same name but are in an earlier search part of the path, they could be injected into your running Go program. So you think you're loading the Windows kernel 32 DLL, but instead you're maybe loading an attacker's 32 DLL. So this is pretty bad. Fortunately, you can use the golang.org xsyswindows package and use the new lazy DLL and new system DLL and new lazy system DLL functions. And these will only consider the official OS installation folders for all those DLL loads. And you should be doing this to call any Windows DLL and call the functions in those DLLs instead of using the Syscall package. This will protect you from this and is much preferred. All right, so once you have a DLL loaded, you need to actually load the function or load the procedure. So we have to pick a name here, and we're going to pick CreateJobObject W to load. So all we do is get the DLL, new proc, and then as a string, put in our function name. So here we have CreateJobObject W. We store the result of that in a variable, usually in the global space of variables, so that you can easily access them from your functions. All right, so we want to create actually a syscall function to call this procedure, but this will involve mapping C types, what the language in which they're defined in the docs, to Go types, the language we're actually using. Now, on the right, you can see a bunch of primitive types and their mappings. Now, this list isn't exhaustive, but it should give you a flavor of what you can expect when doing some of these mappings. Basically, you go to the Windows data types reference that's on that link below at docs.microsoft.com, obviously. And these types are outlined there, and they'll give you hints to what they should be in Go. They'll say, this is a value between this lower bound and this upper bound, and from there you can say, oh, well, this is actually a 32-bit value, and it's not signed, so it's a uint32. For example, a D word is defined like that. Now, pointer types are kind of special in that they're always uint pointers. So if you see a pointer like an LP void or something like that, that's just going to be a uint pointer. Now, actually, pointers to embedded structs we'll get to in a bit. But there's another thing that has uint pointers, and it's actually floats and doubles. And these are used by actually the math package. You have to use the math package to convert using the actual bit interpretation for passing those on to Windows Syscalls. Now, that's kind of outside the scope of this talk, mostly because not many Windows APIs have floating point arguments, so you're probably not going to run into it. But if you do find yourself running into it, see the Go doc for the syscall proc call function. That'll have some more guidance about what you need to do. So let's take a simple example first, the open process function. This takes a lot of primitive types and returns a pointer type. So it takes a D word and a bool. A D word is just defined as a uint32. It's pretty straightforward. A bool is actually defined as an int. And ints are in C compiler dependent. But we know what architecture and compiler we're using, and we know that that actually results in a size of a bool equaling 4 bytes. So we know that it's a 32-bit integer. We also know that it's unsigned, because a bool can only really have 2 valid values, 0 and 1. So a uint32 is a good choice for this, although it may not even matter. So a handle is actually defined as a LP void. So we know from our pointer thing that that translates to a uint pointer. So handles are just uint pointers. All right, let's go back to our CreateJobObject W function. Now this one doesn't really take primitive types. It actually takes a pointer to a structure and a string, a UTF-16 string, actually. So we're going to have to figure out how do we pass these things to this function. So first, we're going to deal with the strings. So how you convert between a Go string and a C string is defined like this. Basically, you tack on the null byte to the end of your regular old string, and you return the pointer to that first element. Now, this is just for regular ANSI C strings that only deal with ASCII characters. If your string is UTF-8, you're going to need to convert that to UTF-16, tacking on that extra null character, and return a pointer to that first element that way. Now, fortunately for you, these are both defined in the syscall package under syscall.byte pointer from string and syscall.utf16 pointer from string. So definitely use those if you need to convert from a Go string into a Windows interpreted C string. However, the reverse is not quite true. So if you have generally a pointer to a UTF-16 string, you're going to have to do a little bit of work yourself. So we know that each character is 2 bytes wide. And we also know that C strings are just defined as an array that is null terminating, meaning we're just looking for a character that's 0 or equal to 0. So what we do in this case is we just iterate using pointer arithmetic through our pointer until we find a value that is 0. And that introduces a null. So once we've done that, we've incremented to the null character, and now we know how many characters are in our string. Once we know how many characters are in our string, we can use the unsafe pointer conversion to convert to a pointer of a very large array that we can then use the slice operation to convert that into a slice. This will allow us to use the native slice operation directly without having to resort to something a bit more complicated, like interacting with the actual slice header. We also have to take care that our slice is a slice of UTF-16 values. So we have to convert that using the UTF-16 decode function to get a UTF-8 representation of that string. And then we can use the result of that as our actual Go string. So struct types are pretty much the same as looking up function parameters. You find out which types the fields are. And if there is an embedded pointer type, if that's a pointer to a structure that you want, you could also define that structure and define it inside of your parent structure or the enclosing structure as a pointer to that structure. So really just pointers are just pointers. In C, in Go, pretty much the same. The other thing you have to worry about is recursive definition of this stuff. So if you actually do want to access the fields of the security descriptor in this example, you need to define the Go type for that, and so on and so forth, until all the embedded types are defined. And that will give you a full object graph of whatever this function, whatever this structure is. So in this example, we have a D word, pretty straightforward. We have an inherit handle, which again, pretty straightforward, it's Win32, but we have a security descriptor, which is actually a pointer to another structure that we just define as a pointer to another Go structure that we would recursively apply this field analysis to. All right, so putting this all together, this is how we would create a wrapper function to call the Open Process API from Go. So we have a function, Open Process, that takes the desired access, an inherit handle, which is a native Go Boolean, and a process ID, which is Uint32, and returns a Syscall handle and an error. So we're doing this with a bool so that we can give our caller a little bit more nativeness to Go, so they don't have to actually do this conversion themselves. We'll do this for them. So we basically take the inherit handle and convert it to an integer, which is either 0 or 1, a Uint32 integer. We then use the process that we loaded, the proc open process, to call that syscall. Now, syscall is called in this way. All arguments are actually Uint pointer args. So every argument we pass to that syscall are in order that the documentation provides and are cast to a Uint pointer. The result of that function returns a return value, which is some Uint pointer, and also an error number. So in order to determine whether or not our function was successful, we have to compare our return value to what we know as the invalid or error value. This will allow us to return the error number instead of the perhaps invalid return value. And then lastly, if we didn't encounter an error, we have our actual return value, and now we can just return that from our function. So that last thing, you always have to inspect your return value against the values the documentation says are valid or not. And the return value is usually documented this way. If the function returns a value of this type, it's invalid, and to get the error number, call the getLastError. Now, the Go library, the Syscall library, actually gives you this getLastError for free. It calls this for you. It's that error no in the previous example. But that's only really valid if we know that the return value is invalid. So we always have to compare using the logic that we found in the documentation. So in the case of a CreateJobObject function, which takes pointers, you can see we're using the Unsafe package to convert a Go pointer to a Uint pointer, because that's just how you call all of these syscalls. You need to convert the pointer types in Go to Uint pointers. But once they become Uint pointers, they're just numbers. And that could be unsafe, since the Go can move these things around at will. So how do we get safety out of this? Well, let's take a look at how Go actually interprets these calls. So the Go compiler understands that passing a pointer to a syscall requires this stable memory location. So when you enter the function, Go is allowed to move memory around. However, if the conversion from a Go pointer to a Uint pointer happens entirely inside the argument list of a syscall, Go will actually lock down that memory for you. In this case, Go won't move it around, and it won't consider it freed. We'll consider it in use for the duration of the syscall. Next, the syscall may exit. That lock is now released, and then Go is free to move that memory around if it wants to again. But you are none the wiser, because now you're back to Go's control flow. All right, so putting that all in your head and trying to do that for every single function you need, that can get a little bit tedious. So instead of doing that, you can instead use the mkwinsyscall function, well, command really, that the syswindows library exposes for you. What this does is it parses your source files for these generator comments, which interpret them as parameter lists and generate function wrappers for them. It also knows some common conversions from some simple types in your argument list to the underlying types that are necessary to call the Windows API, like a Go bool to a Win32 bool, for example, or from a string to a C string or UTF-16 string. In order to use it, you typically have a Go generate statement that runs the mkwinsyscall function, or I'm sorry, the command, and then you give it an output, which the output should be guarded by build tags, or in this case, by the name _windows.go. And you give it one or more input files. These are the input files that the mkwinsyscall command will scan for those sys comments. Below, you can see an example of using the sys comments. We're defining two such functions, one for CreateJobObject and one for GetExtendedTcp. So the first one, we're saying we're generating a function called CreateJobObject, which takes these parameters and emits those output parameters. Now, all parameters that are defined in this way must be named in order for the generator to work. Additionally, if the function name that you want generated does not match the function that actually gets loaded from the DLL, you must specify that after an equal sign on the suffix of this function signature. So in the example here, I'm actually doing equals kernel32.createObjectW. So for the CreateStd handle, we have a different thing where the return value may be invalid, but invalid in a different way than perhaps the default comparison of return values are. So in this example, when a return value is equal to this extra large integer that's defined elsewhere, that's actually what we use to determine whether or not the error null is actually an error and return an error from our resulting syscall. So you do that with square brackets after the function definition. In this case, we're doing fail ret value equals invalid handle. Now that will say if that comparison is true, then the error no will be returned instead of the returned value from our syscall. And here's kind of what a generated syscall function looks like. So it does the loading for you with the new lazy system DLL function. It loads the procedure for you using new proc. It generates the function with all the signatures of your resulting type signature. And it calls the syscall and makes sure to use the uint pointer to unsafe pointer conversion entirely within the syscall arguments. It does that comparison for your return value to see if it's valid. In this case, the default comparison is if it's equal to 0, then it's invalid because 0 is null, and a null return value is typically invalid. So if that's the case, then it will use the error no that it gets from the syscall. Otherwise, it will just return the returned value as if it's a good value. In this case, it's a good handle. All right. The next thing I'd like to move on to is memory management. And basically all the API calls that we've been calling so far, they've been taking primitive types and returning a number. In this case, a pointer or an address, a handle. And this is fine, but there are a lot of API calls that need to return more complex values, and this can't be easily done from C. Because C doesn't really have the advantage of a heap allocated memory model that can be garbage collected. So somebody has to manage this memory. Now, so this means that the syscalls actually come in two different flavors when they need this. They come in unmanaged memory, which means that the syscall actually allocates memory for the caller and then basically passes the responsibility of freeing that memory to the caller. And then there's the caller managed memory, where the caller actually provides the syscall memory in which it can write. So the caller allocates this memory and is responsible for freeing it itself. In Go, this memory would be allocated by the Go runtime, and so the garbage collector would be responsible for freeing it. An example of the unmanaged type we're going to be examining is the Cred Enumerate W function. An example of the caller managed type that we're going to be examining is the GetExtendedTcp table function. So on the unmanaged side, the Cred Enumerate W function will be providing us with memory, and on the GetExtendedTcp table side, we'll be providing that function with memory to be written to. So as an example of our first function, we have this cred enumerate W, and it takes basically these pointer arguments that it will write the pointer address into, and will allocate that memory for you. So you pass it a pointer to an array of credential pointers, and in response, it will write the address that it allocated for you to that pointer that you passed. It will also write the number of credentials into the count address that you've given it, so you know how many credentials that it's given you. It also, in the documentation, mentions that this memory can be freed by calling the cred free syscall. So now you have this memory from the function. When do you free it? Well, you basically have two choices depending on the trade-offs you like to make. First, you could choose to keep that raw pointer around and just use the unmanaged memory directly, and then give your caller the option to free it later. This is potentially more difficult to do correctly. But if you don't want to pay the upfront cost of copying memory upfront, you can use this technique to defer the copy until it's needed. The other type is you can choose to copy memory into Go's managed memory by creating Go structures and copying the data into them. After you're done, you can simply free the unmanaged memory immediately and return the Go managed memory to your callers. I'd advise for this option over the former, unless you have very good reasons for not doing that. But let's take an example of doing it with the unmanaged memory without freeing it first. So how would you design an API for this sort of access method? So here we have a credentials type that we're defining, and we're going to be creating this function to call it and returning this credentials value here. Now, before we get into it, I'd like to point out that the way that our syscall is defined here is with 3 levels of indirection. So be very careful when you're interpreting the documentation. This tripped me up a little bit already, but a pointer to an array of pointers, when you see the word array, it's actually just another pointer. So you're getting a pointer to pointers, and hence the 3 levels of indirection. So let's take a little bit of a zoom in on our credential structure that we defined for this unmanaged memory model. We have our resulting items memory just in a regular pointer here. It's a pointer to credential pointers, which is how we interpret an array of credential pointers. We also have a count of how many credential pointers we have. We also have to keep track of whether or not a memory is freed. So when you're keeping around unmanaged memory, you have to be very, very cognizant of when that memory is valid to be accessed. So we have this memory that we got back from our syscall, and we need to be able to give the caller an ability to free it. So we have this method that we put on our credential struct to free the memory using the cred free function that was defined in the syscall. We pass in our unsafe pointer to our items, and then we also flip our free bit on. This allows us to not free our memory twice. We don't want to double free our memory, right? That would be bad. So we have to keep track of whether or not our memory is free somehow. You also have to document to your callers that they must call this function when they are done with their credentials. Otherwise, this will introduce memory leaks. And memory leaks are not really something that we're accustomed to dealing with in Go, so it has to be documented for your callers. So also another API design consideration is protecting your callers from accessing unallocated memory. So instead of providing, for example, a slice of these credentials back to the caller, we instead want to do something like a for each loop. This will allow our caller to provide a function that will be called for each iteration through that loop, kind of like an iterator function. This kind of makes it more like walking a tree like you would do when you walk through a file system on Go. But this gives us the added benefit of doing some safety checks on whether or not our underlying memory is free before we let our caller operate on them. In addition, our credential type defines field access as functions to its arguments, its underlying struct field that are in C. So instead of giving the caller direct access to a credential name, for example, it will instead use its ability as a function to check whether or not the underlying address has been freed, and if not, then it will do any conversion it needs, for example, converting here from UTF-16 string into a Go string, but it could also return the underlying value if it's, for example, a Uint32. It's worth noting that this conversion from the underlying UTF-16 string to a Go string will actually be done on Go's managed memory. So the resulting string that's returned from the name function here is managed and will be garbage collected, just like any other garbage collected value. All right, so we've done that, but I think an improvement on that design is to use copy and free. It's generally more difficult to misuse this since you'll be returning regular Go structs to your callers. It's safer since there's no more unmanaged memory to remember to free and not use after freeing. It's also easier to code against because your Go structs can just use the convenient types that everybody's used to instead of the underlying C types. Even Win32 is kind of cumbersome to interact with. So let's go back to our example again. This time, our Cred enumerate is going to free things immediately. So instead of returning some kind of iterator type, we'll instead return a slice of credentials, like you might expect from a very well-designed API. In order to do this, however, we need to be able to copy all of the underlying C unmanaged memory into Go managed memory. So we basically have to iterate through every single credential returned by this function and do a conversion to a Go struct. Next, after we have our completed slice of that array, our defer cred free happens on our items pointer, and that unmanaged memory is freed immediately before the call even exits. So the caller just has a regular slice of credentials without any need to remember to free them when they're done with them. The resulting structs that they deal with are also very convenient because we do these conversions to underlying Go types that are very easy to work with. So for example, we convert all of those UTF-16 strings to their underlying UTF-8 representation that's natively workable in Go. We also convert oddities like the Windows time structs into convenient Go time.time structs. And lastly, our embedded slices can just be slices. They don't actually have to be pointers to arrays. So very convenient to work with. Let's move on to the other type of memory management, which is memory managed by Go that's given to the C Syscall. So the general call pattern for this kind of function is as follows. You set up a bufflen variable, a buffer of bytes, and you call the syscall with a pointer to that bufflen and a pointer to that buffer. If the buffer is not sufficiently sized, the syscall returns with some error value like error insufficient buffer. It also writes the expected buffer size to your bufflen variable. You use this information to allocate your buffer to the correct size. You call the syscall again with your newly allocated buffer and your new bufflen. The function may actually have changed its requirements between those two calls, so you have to put this in a for loop in order to detect if that has changed or not. You call that until you either get a success or an error of a different type. If you get a success, now your buffer is filled with a structure that was documented in the API, and you are free to use the unsafe pointer conversions to convert that to a more convenient structure that you've defined. So in this example, after we're done, we use our unsafe pointer conversion to convert this to a pointer to our Win API Go struct that we used the documentation to build. And that is our result. So let's take a look at our example, the GetExtendedTcp table syscall. It expects to be given a buffer of bytes and will fill that table with values. Actually, the type of this table is polymorphic for this particular function. So depending on which parameters you give it, actually determines what structure ends up being in this memory that you gave it. But for our example purposes, we're just going to pick one. I want to get a table of all TCP IPv4 connections and their own process ID. So I pick the values that will give me that, and I call this syscall. So the first thing I do is define the syscall using the mkwinsyscall command. I do this, and I use the function, I do this at the top of our function here. You can see here the GetExtendedTcp table, all the expected input arguments, and since this is not in kernel 32 DLL, I actually have to fully qualify where this function is existing. In this case, it's in the IP helper DLL with the name GetExtendedTcp table. All right. But the other thing is that the mkwinsyscall can't do this for loop generation for us. It doesn't know that we need to recall this function to get a valid value of it. So while we define the boilerplate how to call this function with the Go types, we still need to help it out by doing this for loop ourselves. So the first thing we do is we basically query the syscall to say, hey, I have an empty buffer. What do you think it should be? It comes back and says, well, that was insufficient. 0 bytes is not enough to write anything into. So instead, give me X bytes. It does this by writing into our table size variable. Then we just make a buffer of that size and recall it in our for loop. We put this through over and over and over again until we don't get an error insufficient buffer error. And once we exit this for loop, now we convert the resulting byte slice into something like a slice of table rows. On the next slide, I'm going to go into how we do this conversion. So here we've got a table structure that has some very convenient Go types in it that represent these connections. So a local connection is a net TCP adder. A remote connection, again, a net TCP adder. What TCP state is it in? Basically, is it closed, open, fin, wait, etc. And then because we're doing the owner PID, we actually get a process ID, which we're going to represent here as an int. We convert to this structure by getting the raw byte slice, getting a pointer to the first element of that array, and converting it to the table structure that was defined in the documentation. Now, this type is actually a bit different than what we're used to. The table here has an embedded array. That means that it's not just a pointer to an array that's been allocated in some other area of memory. The array is actually part of the struct. Now, Go can't really represent this kind of thing directly. But what we do instead is we create a type that has that table with one element array instead. This allows us to get a pointer to that first element, which is a pointer to some location that's actually inside the structure. So we do this only if the number of entries is greater than 0. So we can see here we've casted it to this mib TCP owner TCP table owner PID. We get our table out of that. We see how many entries it has. If it's equal to 0, we have no entries, so we should just return immediately that pointer to that first element is invalid. So we don't want to access that memory because it's actually outside of allocation boundaries. But let's say that we do have more than one element. So instead, we're going to make our array of table rows that we want to return from our function. And then we're going to reslice that table. We have a pointer to that first element, so we can convert that to a pointer to a very, very large array and use our native slice assignment trick to get a slice header created for that is right sized to the number of elements in that array. So now rows is actually a slice of those mib TCP owner PID rows. We can use now a range to range over those and assign each element of our result slice to the table row that we've defined in the previous slides. And do all the necessary conversions from the icky Windows types into more convenient Go types. For example, for the IP addresses, even the PID, and perhaps make a special type for TCP states that we can use to do like strings, like to get a string representation of that int, for example. All right, so I covered a lot here of the major points, but it's difficult to fit a whole program on a few slides. So if you're interested in playing around on working code, there is a GitHub repo I'm making available that will contain full examples of all the programs that I've only had partial examples of here. So snap that QR code or visit the link below. It will have a full implementation of basically a netstat command using the GetExtendedTcp table API. We'll have a command to enumerate all of your credentials, both using the unmanaged memory and managed memory variants, and a few examples of doing little point arithmetic type stuff. So if you're interested in learning a little bit more or diving a little bit deeper into what a real program might look like, I recommend that you check that out. And with that, I thank you very much for listening to my talk. Safety may not be guaranteed, but you shouldn't be afraid to try anyway. I hope that you now find the Windows API and interoperating with C a bit more accessible. Thank you.